This lesson is to demonstrate how to solve one-step equations, meaning there would only be one operation in these equations. We're going to use models, and we are also going to use algebra notation. I will tell you ahead of time that all of these equations can probably be solved using mental math. However, I picked equations that were more of an elementary level to show you the algebra notation, because that way you're starting with things that are easy and gradually it will become more and more difficult. But it's always good to take easy equations and apply new skills than to take the most challenging calculus and try to determine that first. For the first picture model, I see an example that is really similar to what we did on a previous set of notes. According to the picture model, I see a variable, x. I see unshaded squares, which will be positive constants or addition, and I see that it's balanced with 7. To use a picture model to solve, our goal is we want to isolate the variable. In order to do that, I would need to remove these 3 constants. However, if I did that, then the balance would tip and it would no longer be equal. If I remove 3 over here, I must remove 3 over here. And then I can see that the variable value is balanced with 4. And if I mentally check that and I substitute a 4, 4 plus 3 does equal 7. Here's how the notation would look if you were doing algebra notation. And this is the part that is new. You would write your equation and think whatever you are doing to the x, in this case I'm adding 3. I want to think of the inverse, the opposite. The opposite of adding 3 is subtracting 3. What I do to one side, I do to the other. I'm showing mathematically what I showed in the illustration. Removing 3 is subtracting 3. From here, if I have plus 3 and minus 3, that would cancel out and make 0. And I'm going to bring down the variable and the plus sign as though I'm performing order of operations. 7 minus 3 would make 4. We know from the identity property that anything plus 0 is equal to itself. So if x plus 0 follows the identity property, that's the same as just x. So we believe that our solution is x is equal to 4. That is consistent with what we got in the picture, and we are going to check. We're going to check our work by using substitution. In a previous video, we talked about substitution mathematically, the way that a substitute fills in for a teacher. When you substitute in math, you fill in values in the place of a variable. How the check process works is you begin with your original equation. You take the solution that you got. In this case, we got the x is a 4, and I'm going to replace that. I'm going to rewrite everything as though I'm solving an order of operations problem. 4 plus 3 would make 7 on the left, and I see that I have 7 on the right side of the equal sign. Because I get a true statement that 7 is equal to 7, that's true, I know that my answer of x equals 4 is correct. In the next example, I see x plus 4 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Using the picture notation, this variable is not isolated right now. There are constants in the way. In order to isolate the variable, I would need to remove these 4. But if I did that, the balance beam would tip. What I do to the left side, I must also do to the right side. According to my illustration, I see that x, now isolated on the left, is balanced with 6. And checking that mentally, 6 plus 4, yes, it would equal 10. To show the algebra notation, I'm going to think about inverse operations. Right now, what I'm doing to the x is adding 4. To undo that, I need to perform the opposite operation, subtracting 4. Whatever I do on one side of the equal sign, take away 4, I must also take away 4 on the right side so that the balance is maintained. Plus 4 and minus 4 would just cancel out and make 0. 10 minus 4 is equal to 6. Anything plus 0 is equal to itself. So there's not a reason to put x plus 0 equals 6. I can just say x equals 6. In order to check my work, I will write the original equation, substitute the solution of 6, and I'll just work the problem forwards again and see if I get the same solution. 6 plus 4 would make 10 on the left. 10 is also on the right side of the equation, and that is a true statement. 10 is equal to 10. Therefore, I know that 6 was a correct solution. For the third one, you might be looking at the balance beam and be thinking to yourself, all of the variables are isolated already. And it's true that there are no constants over here, but I don't want to know what 4 variables is equal to. I want to know how much each variable is equal to. I see 1, 2, 3, 4 x's. 1, 2, 3, 4, 5, 6, 7, 8 constants. 4x, or 4 times x, is equal to 8. So if I want to know how much each one is worth, I want to take these 8 and I want to split it evenly between the 4. I can make 4 groups if each group has 2, which means this variable could be those 2, that variable could be those 2, this variable could be those, and this variable could be those. So each x is equal to 2 squares. And we'll confirm this using algebra. In this equation, I don't see addition the way that we previously had. Because the x is touching a coefficient 4, that means multiplication. The inverse of multiplying is dividing. So if I'm currently multiplying the x times 4, the opposite of that would be dividing by 4. And I'm going to show my division as a fraction because fractions are another way of showing division. And that's also what we did in the picture. We were dividing the 8 evenly between each variable. So I'm taking the 8 and I'm dividing it by 4, how many variables there were. 4 divided by 4 would make 1. I'll bring down the x. 8 divided by 4 equals 2. We also know from the identity property, anything plus 0 equals itself. Also, anything times 1 equals itself. And what you usually don't see in algebra is a coefficient of 1x. 1x is the same thing as just x. And the identity property in mathematics confirms that for us. So each x is equal to 2. We're predicting that based on the illustration, and then we'll check our work using substitution. As you can see, I like to use different colors to represent what I'm undoing. I like to see my inverse work in a different color, inverse work in a different color, inverse work in a different color, just so it pops out to me. And so I see, oh, I did some inverses on the left. I'd better also do some inverses on the right. I also like to show my substitution using a different color, just so it pops out and I can more easily see a 2 because I got a 2. 4 times 2 is equal to 8 on the left, which equals 8 on the right. That is a true statement, so I know that my solution is correct. For the fourth one, we see 3x's is balanced with 3, 6, 9, 12, 15. But we want to know how much each x is. It's true that they are isolated, but we still need to know how much each individual value is. But I can easily see 3 groupings in the constants on the right side. So that variable could have those 5, and that variable those 5, and that variable those 5. So I predict that each value of x is a 5. X is being multiplied by 3. The inverse of multiplication is division. Three divided by 3 makes 1. I'll bring down the variable. 15 divided by 3 makes 5. 1 times anything equals itself. We predict that the solution to this equation is that the x is equal to 5. If I check it using substitution, Three times 5 is equal to 15. And that produces a true statement. So far, we've been able to work through many examples already, and I'm going to add some little notes over here. These 2 problems were addition, and we undid them using subtraction. These 2 problems were multiplication. We undid them using division, inverse operations, and we're going to take a shift moving forward. So in the other examples, we're going to try to do them algebraically first and only use the picture models as another way of checking so that we can try to move ourselves forward. You can't use pictures when you're in pre-calculus, unfortunately, to solve some of those equations. They're much too high level. But the visual is nice when you're just starting out to kind of see what is going on. In this equation, I see a variable, and I see colored in squares, which according to our key represents negative constants or subtracting. 1, 2, 3, 4, 5, 6, 7. So this equation is x minus 4 is balanced with or equal to 7. And we're going to try the algebra first. I see that subtraction of 4 is what's happening to the x. So I'm going to think, what is the inverse of subtracting? The inverse of subtracting would be addition. What I do to one side, I should make sure to do to the other side. Taking away 4 and then adding 4 would have an overall outcome of 0. Bring down the variable. 7 plus 4 equals 11. Anything plus 0 is equal to itself. I predict that the solution would be x is equal to 11, but I'll check it. If I substitute in 11, 11 minus 4 is equal to 7. 7 on the left-hand side and 7 on the right-hand side. So I know that my solution was correct. Now to look at the picture. If you're looking at the picture model and you're thinking, how on earth would I get 11? If you try to take away 4 shaded squares, I don't have 4 shaded squares over here to make them cancel out, to treat one side as I would treat the other. But look at what we did mathematically. We added 4. So I'm going to show adding 4. I'm going to keep them unshaded. If I add 4 to the left-hand side, but I don't add 4 to the right-hand side, then the scale would tip. And if you're still looking at this thinking, Ms. Halpern, the variable is not isolated. It actually is. It doesn't look like it's isolated in the visual, but it is isolated in value, because we know that positive and negative values cancel each other out and have an overall result of 0. And so this would show that one variable is balanced with 11, and that is consistent with what we got using algebra. So I can undo subtraction with addition. For the following one, I see x plus 2 is balanced with -5. Again, we're going to try to use the algebra first and then use the picture model as another way of checking. In this example, I see that 2 is being added with x. The inverse of addition is subtraction. Adding 2 and subtracting 2 has an overall result of 0. -5 minus 2 more would be -7. I know this because I'm imagining on a number line, go backwards, 5, keep going backwards, 2 more. And anything plus 0 is simply itself. As you can see, when you get into higher level equations, checking processes and multiple ways of solving become more important because you may not be as good with negative numbers as you are with positive numbers. We predict that the x value is a -7. let's check it. -7, and if you add on 2, would that really be -5? And I can use a picture model if I'm not sure about this. 7 negatives, 2 positives. These would cancel, and I do see 5 negatives left. Since we got a true statement, the answer of -7 is correct for the value of x. To show it using the picture model, we subtracted 2. Subtracting 2 is shown with the shaded in squares. And even though it looks like I'm adding on things to the picture and not crossing things off, keep in mind that the only way I can show to put on negatives is by coloring them in. Positives and negatives will cancel each other out, and the result is 0. And I can see that one variable is balanced with 7, and that is consistent with what we already got. In the next one, I see a variable and I see it being cut in half. And when we've seen this on previous activities, cutting something in half means division. And it's balanced with 5. Again, we're going to try to use algebra and go back and check it with a picture. If the variable is being divided by 2, the inverse of division is multiplication. I'm using a dot instead of an x because I don't want that to be confused with the x of a variable. If I divided something by 2 and then multiplied it by 2, kind of like over here, multiplying and then dividing, I just had a result of 1. Five times 2 would be 10. Anything times 1 is equal to itself. So we believe that the value of the variable is 10. To confirm that, I'll take a 10 and substitute that back into the original equation. 10 divided by 2 is equal to 5 on the left, balanced with 5 on the right. I get a true statement. And if you're looking at the picture and thinking, how am I going to show that the x is equal to 10? Well, this part of the variable is those 5. The other half of the variable would also have to be 5, meaning the entire variable is in fact 10. In the final example, we see a variable and it has been cut into 3 pieces, and these are shaded out, and we're only focusing on this part, or that third. So we're showing x being divided by 3 on the left, and it being equal to 3 on the right. When I do my algebra work this time, I'm not going to represent division using the division symbol. I'm going to represent division using a fraction because that is another appropriate way to show division. X divided by 3 is equal to 3. If we are doing division, the inverse operation would be multiplication. Dividing by 3, the opposite would be multiplying by 3. When you look at this notation, it's a little bit easier to see why you would get 1x. Imagine 3 times x is 3 x's. 1 times 3 is 3. 3 x's over 3. These could be simplified out if you divide each one by 3 to get 1x over 1, or just 1x. But in my mind, I know that if I divide something by 3 and I multiply it by 3, those essentially cancel each other out to just leave me with 1x. But this is more the mathematics that's happening behind the scenes. And 3 times 3 is equal to 9. To check, I will substitute the 9 for the x. Nine divided by 3 is equal to 3. And I do get a true statement, so I know that x's value is really 9. Just to confirm, using the illustration, this third is those 3. Another third would be 3. Another third would be 3. The entire x, the entire variable, is now balanced with 9, and that's the solution that we were predicting. Our notes are now complete about how to solve one-step equations. I'll add one final note on these two, that we undo division problems with multiplication. As you can see, the big ideas are still holding true. What we do to one side, we do to the other side. We're using inverses, and our goal is to isolate the variable and find out how much each individual x is worth. We've now also incorporated checking our solution by writing the original equations and taking our solution and substituting that in the place of the variable and working it forwards again and making sure that we get the solution that we should be getting. Eventually, you're going to say goodbye to the pictures and you're only going to be focused on the algebra. Even though many of these are equations, for example, x plus 3 equals 7, you know in your mind that that is a 4. It's just showing you the proper algebra notation, how you perform inverse operations on both sides of the equation, and how the number properties are working to say it's okay that you go directly from x plus 0 to simply x because of the identity property and things like that. Thank you for being patient and watching a really, really long video, but it goes step by step and incorporates addition, subtraction, multiplication, and division problems with all the algebra notation that you are going to need.